Hello again. So here we're going to introduce Charles' law and the coefficient of thermal expansion. Now, Charles' law is probably most well known in this form where we show the volume of some object. He was dealing with gases, mostly air, is going to be proportional to temperature. And this value K is a proportionality constant. So we need this constant here to convert the units and then to make the things equal. Obviously, V is not the same as temperature. So what is K? K is this constant that allows you to think about how volume might change as a function of temperature. So if you have volume increasing on the vertical axis and temperature increasing to the right, then there would be some slope to that line, and K would be the slope, the thing that would relate those two variables, volume versus temperature. So we did experiments to suss out what K might be if you had various kinds of substances, especially air. But Charles did something else. He wrote a different equation as well that introduces this idea of a thermal expansion coefficient. The coefficient of thermal expansion is the way it's normally expressed. So let's say we have some volume at some initial temperature T naught. Let's let T naught be equal to 0 degrees centigrade. So we can imagine that you have, let's say, a crystal of olivine. And that crystal of olivine, of course, it would not naturally grow in a shape like this. But this is a very easy shape to draw, and so we will. You've taken a bit of olivine, you've carved it into a cube, and let's say that cube has an initial volume of 10 cubic centimeters, 10 cc's. And let's say we're going to heat this thing up until it expands to some larger value, some larger volume. And so it looks like this. Now, it might be the case, and sometimes it is, that you want to calculate what that degree of expansion is. How do we get from the blue to the white, right? So we go from an initial volume V naught to some final volume, and we'll just call it V. Let's take a particular temperature of 1,000 degrees centigrade. So V naught is going to be, just by definition, it's going to be 10 cc's. And the equation that Charles developed is this, that the volume at 1,000 degrees centigrade is going to be equal to the initial volume plus a correction. And the correction is that initial volume multiplied by this coefficient of thermal expansion, so that's alpha here, multiplied by the change in temperature. So alpha is the coefficient of thermal expansion. Now, I've given values here. We've said that we'll take a sample of olivine because I want to run through just a simple sample calculation. Let's erase the chalkboard and rewrite Charles' law. So it looks like this. We have the volume at 1,000 degrees centigrade would be the initial volume plus the volume times alpha delta T. This thermal expansion coefficient is a measure of how quickly a material will expand or contract when it's heated or cooled. Things that are loosely bonded might have a very large alpha and they might expand very rapidly when heated up just a little bit. On the other hand, if you have things that are tightly bonded, you might have a very low alpha. Well, the alpha for olivine is about 3 times 10 to the minus 5. And the units on this are 1 over degrees centigrade. And you can see why we need those units. We've got volume here. We want volume as an output. And we're okay with units of volume here. And we have units of volume here. So these units need to cancel. If the temperature here is in degrees centigrade, then we need something of units 1 over degrees centigrade. So those can cancel, just leaving the volume. So the units of alpha are given by the nature of the way Charles expressed this equation to calculate a volume change. So let's do that kind of calculation. Let's say your little block of olivine has been sitting at in the freezer at 0 degrees centigrade. So the delta T, if we heat it up to 1,000 degrees, would be 1,000 minus 0 equals 1,000 degrees centigrade. And so if we put that into this part of the equation here, we would get that the value for the volume at 1,000 degrees centigrade of olivine is equal to our original value. Remember, we said we were going to use 10 cubic centimeters plus 0.3 cubic centimeters. So it would be 10 multiplied, this value here is 10, so it's 10 multiplied by 1,000 multiplied by 3 times 10 to the minus 5, and so it gives us 0.3. So the final volume after heating is 10 cubic centimeters, or a little cube of olivine is increased 0.3 cubic centimeters in volume by heating it up from 0 degrees, taking it out of the freezer, and then putting it into an oven where it's heated up to 1,000 degrees centigrade. So that's not a very large increase in volume, and that's because we have a very small value for the coefficient of thermal expansion. And it just reflects the fact that it's a solid, it's a mineral. It has fairly strong bonds between the magnesium, silicon, and oxygen atoms. And so heating it up isn't going to cause a very large expansion in the volume. But this is the way we would calculate this kind of volume expansion in a very simple way using Charles' law. So just to put it in very general terms, we can have a volume at any temperature as a function of the initial volume and then a correction factor. So we take the initial volume and then we add the initial volume multiplied by some coefficient of thermal expansion and the temperature range, the temperature of increase or the temperature of decrease if we were to cool something and it were to get smaller. And that would give us the final volume, provided this alpha is constant. It's not always going to be constant, but for many applications, it's close enough to constant to solve a lot of practical problems in thermodynamics and geology.